For question number 1, draw the resource allocation graph RNG for the situation above. Explain whether deadlock occurs or not. Okay, for this is resource allocation graph for our group. So for my part, I will explain about the the process of the resource allocation graph. So P1 holds 1 unit of R1 and P1 requests 1 unit of R2. And then P2 holds 1 unit of R2 and requests 1 unit of R3. And then P3 holds 1 unit of R3 and P3 requests 1 unit of R.
Resource allocation graph. P4 holds 1 unit of R2 and requests 1 unit of R1. P4 holds 1 unit of R2 and requests for 1 unit of R1. P5 requests 1 unit of R2 but is currently waiting.
Assalamualaikum and hi everyone. I'm Aiman Shamil and today I'll be explaining what deadlock is and how it happens in the system for question 1. So basically, deadlock occurs when two or more processes are waiting for each other to release resources and none of them can continue because they're all stuck in a cycle of waiting. So in this particular case, deadlock doesn't occur because there is a cycle in the resource allocation graph, meaning that each process is holding a resource that the other needs and no one can proceed. So that's how deadlock is detected and why it is dangerous in resource allocation.
Prevent a deadlock, we can apply one or more of the following strategies. Number one is prevent circular wait or resource ordering. Idea is to tell the processes to request resources in a fixed order, like R1 and then R2 and then R3. If they follow this order, they won't get stuck in the circular wait. For example, if P3 is holding R3, it shouldn't ask for R1 before releasing R3.
Okay, so for question 1, for the second idea, to prevent the deadlock, we need to request all resources at once. So first, we want to make processes request all the resources they need at the beginning. If they can get everything at once, they wait until they can get all the resources. This to avoid holding one resource while waiting for others. So it can prevent from the circular wait. So that's it for second.
Okay, hello, my name is Aaron Azri bin Kamarul Azman. So I will be explaining question 1. This is question 1. I will be explaining further regarding the ways of prevention for deadlock. I will be explaining on point number 3, which is the preemption of resources. So the idea of preemption of resources is if a process holds some resources but can get all of them, we can take back the resources from it and give them to other processes. This can help break the cycle and allow progress. So I'll be explaining in the form of an example. So let's say a system has three processes, A, B, and C. So let's say A is requesting resources from C and B is requesting resources from A. So in this particular scenario, deadlock can occur, has a very high chance of occurring because that first of all is circular and there is the concept of hold and wait. So to allow this not to happen, we can allow so let's say A was requesting from C and B is requesting from A. But let's say in the process of requesting from C, A does not immediately receive the resources it needs to complete the process of process A. So we just allow A to release its resources to a process which is able to be completed within that time frame, which is B requesting from A. So we do not need to wait from A receiving from C. So that is basically the concept of preemption.
So for the last one is no hold and wait. idea, a process shouldn't hold any resources if it's going to request more. If it wants something else, it has to release the resources it's holding first and wait until all the resources it needs are available.
So next is question 2A1, which is about system X, which has 6 devices in total. So our task here is to calculate the need for each process, and the formula that we use is need is equal to max requirement versus allocated. So let's go through the process one by one. So for process A has allocated 2 and the max is 4. So the need is 4 minus 2 and is equal to 2. For process B has allocated of 2 and the max is 5. So the need is 5 minus 2, which is equal to 3. For process C has allocated of 0 and a max of 6. So the need is equal to 6 minus 0 and equal to 6. And finally, for process D has allocated of 1 and a max of 2. So the need is 2 minus 1, which is equal to 1.
For question 2A2, system Y has 15 devices. So for process A, the device allocated is 5 and max requirement for process A is 7. So B, device allocated is 5 and max requirement is 6. For process C, device allocated is 4 and max requirement is 9. So we want to calculate the need of the system Y. So for process A, first to calculate need, we need to max we need to minus the max requirement with the allocated one. So for process A, 7 minus 2 is 2. For process B, 6 minus 5 is 1. So for process C, 9 minus 4. So the need is 5.
So, as Aaron and Pat has explained, it's wrong here because X is unsafe. Yes, I know what I say. Because we can see for system X, we can find the available first. Aaron has find the available is 1. And we can compare all the need items at X is bigger than 1. So the X is unsafe. But for the system Y, the available is also 1. But as you can see, for system Y, we have process P that has need items 1. So we can enter the B first. So and allocate the 5 into the available, becomes the new available, and later on it could be available for process A and C to proceed. So system Y is safe. So the conclusion here is system X is unsafe and Y are safe. Thank you. Next, I will pass to the next person.
So, I will be explaining for question 2. I'll be explaining further for question 1. Specifically, B, which is whether to determine whether X and Y is safe or unsafe. So basically, what you have to do first is calculate the total number of devices. For question 2, so I'll be focusing on X. So X has 6 devices, and then after that, you have to minus the for each process the devices or processes or resources allocated for each process. You total them all up, and then you minus the total number of devices available. So in this example, for B, it's 6 minus 2 minus 2 minus 1, which leaves you with only 1. So there's only one resource left. So you have to see if there are any processes in the system X. You have to look at the need, which is this area. See if there are any processes that are able to run with only one resources. So there are not. So there are only 2, 3, 6, and 2. So no, there are no there are no processes which can be finished with the remaining one resource. So system X is unsafe.
So for system Y, the total device are 15. So the available space is 15. We minus with 5 plus 5 plus 4. The total is 1. So process B can finish first, then A, then C. So the conclusion is system Y is safe.
So for question 2, I will explain one of the answer for question C. If the system is in a safe state, list the sequence of requests and release that it will make it possible for all process to run to completion. So for system S, the system is in a safe. So the safe sequence for system S is D, A, B, C.
Question C. If the system is in a safe state, list the sequence of requests and releases that it will make it for all the processes to run to completion. For safe sequence for system Y is going from B and then A and then C.
Okay, so in this question number 3, I will be explaining the first step in calculating available memory. And if the request for process E can be granted. Okay, so from what we understand, how do we calculate available memory? I mean, calculate remaining available memory. Okay, so we'll start with based on question 3, we know that the total memory before any process is done is 170 units of memory. So to calculate the remaining memory, we have to calculate the total memory minus with the total holding memory for all of the processes combined. So as you can see in step 1, the total memory in a system equals 170 units and the memory allocated to all processes is 110. So what you do is you take the 170, which is the total memory, and you minus it with the total memory hold of all processes involved in the system. So the remaining would be 60. So in the prompt given, process E is given an initial need of 30 units. So with that, 30 is within the parameters of 60. So as per the question, yes, request E can be granted.
Okay, so now we'll continue with question 3, step 2, which is to calculate the need matrix using the Banker's algorithm. So the need for each process is calculated using this formula, which is need is equal to max versus whole. So let's apply that to each process. For process A, max is equal to 50 and the whole is 35. So the need is 50 minus 35, which is equal to 15. For process B, max is 80 and the whole is 45. So the need is 80 minus 45, which is 35. For process C, the max is 60 and the whole is 20. So the need is 60 versus 20, which is 40. And for process D is max is 40 and the whole is 10. So the need is 40 minus 10, which is 30. So now a new process E, requests 30 units of memory. Earlier we calculated that the available memory is 60. So if we grant 30 units to process E, the remaining available becomes 60 minus 30, which is 30 units. We also know that process E has a maximum need of 80, and since we already granted 30, its remaining need is 80 minus 30, which is 50 units. So that completes step 2.
So for question number 3, I will continue my part on step 3. Check for a safe sequence. A system is in a safe state if there exists an order in which all process can finish. So for step 1, a process can be completed if it needs lower than or equal to available. So for step 1, process A needs 15, which is lower than or equal to 30. So A can complete. So after A finish, available memory is 30 plus 35, which is the 65.
Process B needs 35, which is less than equal to 65. So B can complete. After B finish, available memory equal to 65 plus 45 with allocated 1 equal to 110. So the third step, process D needs 30, which is less than equal to 110. So process D can complete. After D finish, available memory equal to 110 plus 10 equal to 120. So
we continue for the process C and E. So as Mansam has explained for B and D. So for process C, it needs 40, which is less than 120. So C can complete because the 40 is less than 120. So after C complete, it will add the allocate device or allocate items into the available items. So becomes the new available item 140. So the last one is process E. Supposedly after C has D, but the D is finished. So after C we go to E, the last one. So process E needs only 50, which is less than 140. So E can complete. So when E can complete, the available memory will change. So the allocate memory of the allocate device of E, which is 30, will added into the 140, becomes the 170. So the available memory will be 170, the last one. So next one is part. Thank you.
Step 4, show the sequence. Since we found a safe sequence from A to B to D to C and then E, which means yes, the request by process E can be granted without issues.
So the explanation of deadlock detection algorithm. For step 1, we need to calculate the available vector. So available vector equal to total resources minus allocated resources. So now we plus all the total resources, total allocated resources for resource 1, 1 plus 0 plus 1 plus 0. So the total is 2 for R2, 1, 0 plus 1 plus 0 plus 1. So 2, R3, 1 plus 0 plus 1 plus 1. So 3. So available vector right now is 3 to 4 minus 2 to 3 equal to 101. So the available vector, the answer is 101.
So for the last question, step 2, apply the deadlock detection algorithm. Process 1, request by P1 110. Compare P1 request with the available resources 101. R1 1 lower than or equal to 1? Yes. R2 1 lower than or equal to 0? No. R3 0 lower than or equal to 1? Yes. Since P1 is requesting more of R2 than is available, P1 cannot proceed at this moment. Sorry. Yes. So let's do the next part.
For process 2, the request is 2, 0, and 1. If we compare P2 request to the available resources, which has 1, 0, and 1, resource 1 needs 2, but it is more than 1. So it cannot be requested. R2, 0 is equal to 0, so it can proceed. R3, 1 is equal to 1, so it can proceed too. Since P2 is requesting more of R1 than is available, P2 cannot proceed at this moment.
Okay, so I will be explaining further for whether what happens after process 3 and process 4 in question number 4. So as we have stated before in the prior explanation of step 1, we have to calculate the available vector. So we have stated the remaining vector will be 101. So back to my part of the question, which is process 3. So the request done by P3 is 101. So we may have to compare the R1, R2, and R3 of the vectors for P3 and the remaining vectors. So R1, 1 is less than 1 or equals to 1. So yes, R2 is also less. R3 is also equals to. So P3's request is less than or equal to the available resources. So P3 can proceed. So we always have to remember after a process has been done, it will release the current resources it holds. The resource could be whether it could be devices, vectors, or resources. So in this particular example, the allocated vectors P3 will be 101. So you add that 101 to the previous remaining vector, which is also 101, leading to the current remaining vector to be 202. So we move on to process 4. So the request done by P4 is 110. So what we have to understand is, again, we have to compare the remaining vectors to the request done by P4. So R1, 1 is less than 2. Yes. However, R2, 1 is not less than or equals to 0. It is more than 0. So no, process 4 cannot proceed because there is not enough resources to fulfill the requirements needed by process 4. So P4 cannot proceed at this moment. However, if there are other processes, then we have to reevaluate process 4 at a later time.
Okay, for question 4, step 3, process 3 or P3 has already been allowed to proceed and it already has released its allocated resources. So now the new available vector is 202. So next, we recheck the status of the other processes to see who can proceed next. For the rechecking of process 2 or P2 request is 201 and the available resource is 202. So let's compare each resource. For R1, 2 is less than and equal to 2, so that's okay. For R2, 0 is less than or equal to 0, so that's also okay. For R3 is 1 is less than or equal to 2, and that's okay. Since all requested resources are available, P2 can now proceed. P2 was holding 010, so after P2 finishes and releases, the new available vector becomes 202 plus 010, so it is equal to 212. That's the updated availability after P2 completes. Thank you.
So next we go for recheck process 4, P4. Now we check P4 again with the updated available resources. So P4 request 110. We compare with the available resource 212. So we compare 110 with 212, which is 1 less than 2 can, 1 less or equal 1 can, and 0 less than 2 so can. So all these three is acceptable. So since P4 request is less than or equal to available resource, so P4 can proceed. So it is allocated by P4, which is the allocation in P4 is 011. So we will add the allocation with the available vector 12 plus 011, we get the new available 223. So then we go to check the P1, process 1. So we recheck the P1 with updated available vector, which is 223. So P1 is requesting 110. So we compare 110 with 223. So 1 less than 2 can, 1 less than 2, yes, and 3 1 less than 3. So yes, or can. So these three is acceptable. So P1 request is acceptable with the available resource. So P1 can proceed. So the allocation in P1 is 101. So since it can proceed, we will add the allocation of P1 into the vector. So 223 plus with the allocation 101, we will get the new available vector, which is 324. So thanks. Next, I will go pass it to Fahad.
So for the final result, all process P1, P2, P3, and P4 can eventually proceed. There is no deadlock in the system. All process will eventually complete their execution.